Thank you very much. And first of all, I'd like to thank the organizers for organizing such a great program and conference so far. It's been great. And also, thank you for allowing us to come and show you some of our most recent results, in which we've heard already about some of these instabilities that are driven by radiative losses. And a lot of people have already heard me talk significant amount of times on this electron-cyclotron maser instability driven by synchrotron losses. But what I'm going to try to convince you of today is that some of these processes can actually be driven and studied in the laboratory using wake-field accelerators. And so in a sense, I want to say that maybe we can do FRB-like emission in the laboratory. And so just stay tuned until the end of the talk for that. We've already heard that there's a whole slew of instabilities. So if you were watching this morning's talk, Aggie was presenting on synchrotron cooling instability and how that can give rise to these regions of low beta plasma and a high beta plasma. There was also the work of Blaimius Duncan on synchrotron fire host driven by synchrotron losses. And these are initially high beta instabilities. And so what I focused on for quite a lot of time, so for the past couple of years, has been on studying the electron-cyclotron maser driven by these synchrotron losses. And I'm not going to go into too much detail because I want to talk a lot about the laboratory aspect of this. But what's interesting about radiation reaction is that it emits part of it doesn't radiate just energy, it radiates away part of the entropy of the system. And so this is able to drive it into kinetic unequilibrium. And so for all of these instabilities, what happens is you're driving away your pressure isotropy, and so you're driving different kind of instabilities. And what's happening in the maser case is that particles that have much more energy than lower energy levels radiate much more significantly. And so what you end up getting is that they all end up bunching up in energy. And so you end up getting these kind of ring distributions in momentum space, which are unstable to the maser. And the maser is interesting because, as the name indicates, it implies amplified stimulated emission, so it's going to produce coherent radiation. What I find fascinating about this is that there are environments in the universe where you have very, very strongly magnetized plasmas, and we do see coherent radiation coming from them. And for the laboratory-minded people, measuring coherence in Kelvin might sound strange, but basically what we measure in astrophysics is you measure a frequency band, you know the specific intensity there, and so from there you can say what would be the equivalent black body temperature that will give me such an emission. And if this temperature is absurdly high, then it means that there has to be some kind of coherent process. And we do observe emission from compact objects. Now we know that pulsars can emit coherently, and we know that FRB, some of them may originate in the magnetosphere of magnetars. Where exactly is still open to debate. And so, without going into too much detail of this instability, what occurs, as I highlighted, is that we're going to cool down particles, and they're going to bunch up in momentum, and they're going to drive this coherent amplification. All of this happens in momentum space, and I'll come back to that in a second, because there's other configurations, other kind of spaces where these instabilities can arise. So here I'm showing you the momentum space of the plasma. It looks a bit empty right now because it's very diffused. All the particles are spread out at very high momenta, but as we let it cool down, the magnetic field makes them gyrate and radiate, and then they show up in our box eventually in the region that we're looking into. And we see that this ring becomes unstable because the plasma doesn't like having these kind of setups. There's going to drive kinetic instabilities to diffuse these rings. The process is quite complex, and I don't have time to go into, but you end up getting emission at the harmonics of the cyclotron frequency. So this is a time spectrum of the radiation. This is a 2D particle in cell simulation. I should have said that already. And you see that the emission occurs at the resonances, as we expect from the theory. If you look at the electromagnetic field energy stored in the system, you see that it grows exponentially. This is a sign of coherence also, and this is from the theoretical prediction from our model. And then finally, you see that the radiation in the box peaks very rapidly and in the polarization degree, and you get very linearly polarized radiation, because what we're exciting here is an X mode. If we let the simulation continue, you see that this ring is sustained for quite a long period, it's not immediately diffused, and you see that the emission bands are still quite narrow for quite a long period of time. there is some oscillation in the saturation amplitude, but this dip is explained by gyrotron devices which operate by the same principle. So we know the maser very well. It's a very old instability, and in fact, coherent sources of radiation in the lab operate via this process. So we have a very good understanding of how this saturates. And then what's interesting also is that the saturation level is not, it is small compared with the guide field, but it is not negligible. So we're getting radiation with a comparable amplitude to the guiding field. And so if you apply this to astrophysics, you are able to produce some very high intensity radiation. And so I usually get the question of where does this how can we even get this setup if we already have to cool down the plasma? And so here I have kind of a cartoon explanation or a cartoon of where does this, how can you heat up the plasma beforehand. So you can have some kind of ejecta in a neutron star. This is going to cool down very fast because we're very close to the neutron star surface. And then as this plasma propagates outwards, it's going to bump into regions where the magnetosphere is not this perfectly straight dipole. If you zoom in, there should be some perturbations in there. And so these are going to non-resonantly scatter and non-resonantly heat up the plasma, which is going to, there is an equilibrium that one can derive also when you have synchrotron losses. And then from there, you are able to obtain how this plasma is going to heat up. Then eventually, just out of sheer luck, in some cases, you can bump into a region where the magnetic field lines are slightly straighter. So there's a bit of a calmer region after this region that's able to heat up the plasma. And in that case, then you can cool down, and when you cool down, you can undergo this kinetic instability. And so that's what I have for the astrophysicists in the room, because then the next part would be how can we study this in the laboratory? And so one of the ways that we could do this is we can produce these ring distributions in the lab directly. So there's a way of imprinting using laser ionization. We can imprint the polarization angle of a laser into a plasma, and that lets us study this instability. So also lets us study like the fire hose instability, and we're looking into other kind of setups that one can do. But then you might be wondering, can we do the whole thing? Can we go from B to C in the laboratory? Can we have a hot plasma that cools down and produces a ring distribution that's going to undergo this kind of coherent amplification process? And so the answer to that question is yes, but. And the but is that there is no magnetic field strong enough on Earth that can produce the cooling that we need in the timescales that we need for this to be important. So for that reason, one needs to think in a bit of a different way, and this connects with some ideas that were derived in the 90s as to how the ion channel laser, free electron lasers, and masers operate. And it's very nice, the theory is very nice, because it combines all of these processes that we know should happen, and free electron lasers, we use them all the time to produce coherent radiation. So the fact that all of them have a unified theory tells you that there are scenarios where we can study all of these processes combined. And so what we're going to do is, instead of having a magnetic field that is going to provide the centripetal force for the gyration, what you do is you have a region with high charge, high positive charge. It's going to provide an electric field pointing outwards, and that's going to provide the same centripetal force. And that we can do in the laboratory. It's called an ion channel, and this happens whenever you shoot a laser or a beam into a plasma. You blow out electrons, the ions don't have time to move, and then your beams undergo these betatron oscillations, which you've heard about several times already. And so as electrons oscillate up and down, they emit radiation. It's called betatron, but it's synchrotron just for this trajectory. And then these can produce beam distributions that are funky looking. They're not these Maxwellians that we had initially. And when this happens, then you can actually trigger this ion channel laser instability, which is the cousin of electron cyclotron maser instability, but in the ion channel instead of a magnetic field. In this case, we're not looking at momentum anymore, momentum space, we're looking at the phase space. So we have radial momentum versus radial position. And so how we're going to do this is if we can compute how the cooling is going to occur. So we have here our driver that has blown out a region of the high density plasma. We need quite high densities, but doable in the laboratory. It produces your bubble. If we are on the back of the bubble, if we have a beam here or an electron here, it's going to feel a force pointing forward. It's going to be accelerated. This is how Wakefield accelerators work. If our beam gets too far ahead, it's going to be decelerated. But if our beam is off axis, it's going to undergo these betatron oscillations, and it's going to radiate a significant amount of motion. And so that's what we have here, this first term. combined with this is just a harmonic oscillator with characteristic frequency of this Betatron frequency. But then if we add up the radiation term, this is all computed from the Landau-Lifshitz formulation, you end up getting just a damped harmonic oscillator that you can solve. There is a nonlinear term, which is a bit annoying, but there are ways to solve this analytically. And I apologize to any Russian speakers in the room, in case, but we use the Krylov-Bogolyubov method. I hope I pronounced that correctly. And in this manner, you can obtain a very good approximation of the trajectories of these electrons in these structures. And you find that they undergo sinusoidal motions, but that your amplitude is actually changing as a function of time. They're being damped. And as that occurs, now that we have this, we can actually write a kinetic equation for our beam, which is going to work in amplitude and phase. So we're working in momentum versus radial position. And so this is just a radial position in these diagrams, and the phase is just gyrating with this Betatron frequency. This equation can be solved analytically, so we know how any beam, given its initial phase space configuration, is going to evolve over time. And so once we shoot beams that are spherically symmetric in phase space, this is a beam that's like matched to the Betatron oscillations of the channel, and this is a beam that's not matched. So this beam is going to oscillate in envelope as it propagates through, which means it's going to gyrate in this phase space. If we let it propagate through, we see that we form these rings in phase space, whereas the other one kind of gets phase mixed. You still form this kind of ring structure, but it's more of a spiral right now. And if we look now at the amplitude, so the distribution function as a function of the amplitude, now we see that we're forming regions which have bunched up in amplitude of oscillation. So these regions are going to be unstable to the kinetic instabilities, like the ion channel laser. For the case that's not emittance match, this is the proper term, this beam that wasn't perfectly matched to the natural oscillation of the channel, you see that you still get a region, but it's not as good. And in fact, you see some features that, so this is what we'll look in if you were to integrate spatially. This is what happens when you integrate in momentum. So this is the profile of your beam as it's in the accelerator, and this is the profile of your beam when you are not perfectly matching the conditions of oscillation. So you see some weird peaks happening as you go further. There is a time scale for this to happen, and we can compute that analytically very nice. And we see that this happens within centimeter scales in a relatively high density wave field accelerator for high energies and for relatively small spot size. And so we can test this. We can take the parameters that something like the Facet 2 experiment would provide in SLAC. So we take the accelerator beams, we provide a high energy, high density plasma, and then we have a driver beam that's going to drive this blowout cavity, and then on the back we have a witness beam. They look quite diffuse right now because they're going to focus due to the forces of these channels. And I have two simulations, one without radiation reaction on the left, and one with radiation reaction. And what you see is that this beam is driving this blowout structure, which is very nice. And then on the back, you see that the witness beam is oscillating. And as it oscillates, you see some bunching occurring. You already see here some radial structures that are not present in the case without radiation reaction. And so this is a clear signature that what we're seeing here is not to do with just the usual beam dynamics, but we have to take into account the radiative losses consistently. And eventually, we're going to run out of energy in this driver, so we're going to have to end our experiment after 5 millimeters of propagation in a high-density plasma. And when that happens, we see that the structure survives exiting the plasma. If we look at the phase space of this witness beam at the rear, we see that we have formed this spiral structure, just like the theory predicted, and we can then also produce the distribution function as a function of amplitude of oscillation, and we see that we have a positive gradient here. So these beams are going to be unstable to the ion channel lasers. If you're an experimentalist, you may be wondering how can we then see any of this? And so what one can do is one can shoot several times with just a driver beam. We can take a luminescent screen, so this is just a screen that tells you integrates longitudinally your beam. And doing this, you are able to take your background shots. Then you are shooting with the witness, and you can subtract one from the other, and you will be able to see the profile of the witness. And what you will see when you do this is that you have these, I don't know how well they show up on okay. You can see some of these halo structures around the central spot size, which are not present when you don't take into account radiation reaction. Moreover, you can take a spectrometer, so this is kind of the divergence as a function of energy, and you'll see some of these bunches which correspond to the same bunches that you see here. So this tells you what's happening in momentum, and this tells you what's happening spatially. And I promised that these beams can produce coherent radiation in the laboratory and that these are connected to the electron cyclotron maser. And so one simulation that we did quite recently is shooting these beams in a very high density ion channel. So we're going to radiate a lot of energy and we're going to form a very interesting structure in phase space, which is then going to be unstable. So we have this beam, as it goes through, it gyrates quite a lot, and you are forming this spiral pattern. I'm going to zoom in several times because we're going to radiate a lot of perpendicular momentum, and you see very nicely that you're forming this ring. And eventually, on the right-hand side, I'm plotting now the density of the beam as it goes through the ion channel. You see that there is some phase bunching occurring here, and you see it in space, forming these bunches in space. So these are very similar to the structure that you form in the free electron lasers. And this produces coherent radiation, and this has only been like 5 millimeters of propagation in a high-density ion channel. And this is also, I should also highlight that this is within current experimental capabilities that we have. So we can do these plasma densities, and we can do these kind of energies from accelerators. And so with that, I took relatively fast, but that gives me a bit of time to go through the conclusions. And it's that I wanted to highlight that there is this zoo of instabilities that are starting to appear that are driven by radiative losses. And some of them are in the high beta, and some of them are in the low beta. And some of them can be important to explain, as we saw, some of the, maybe the galactic filaments, as this was said in the morning, but maybe also the coherent radiation that we see in some astrophysical phenomena. Moreover, we need to come up with ways of testing this in the laboratory, and so what we're proposing here is a way of testing this maser driven by synchrotron losses, but we're going to do it with its cousin, which is the ion channel laser in a high-density ion channel. And with that, I'm happy to take any questions.
Questions?
Hi. So when you said for the experimenters, you would have a screen, you would look at the, was it the electron beam that you were looking at?
Yes. So
I was just wondering, in addition to that, you would be changing the radiation that's coming out as
exactly.
well. So what would you expect? So the spectrometer is for the electrons, right?
Yes, yes. So you will be, yes, so this is the spectrum, and as you can see, it's quite different when you have radiation reaction.
What photons would come out, I guess?
Exactly. So this we can compute, and you will see this, each band is producing a coherent metatron in its own. You see, all of these electrons are oscillating together.
So what frequency is that?
Well, it will depend on the exact when. It will change over time as these are cooling. So you'll see this upshift over time. So what the spectrum looks like exactly, I haven't computed that, but I can tell you is that each bunch will produce its own spectrum.
Other questions?
Which range what? So it will be at the harmonics of the betatron frequency. So for high density plasmas and for high energy beams, you can tune that. So because it's only a question as to what is the density of your plasma. So we can go quite high. So we can go ultraviolet if we want.
Can I ask you a very quick question? So in your simulation of forming this ring, I think you said it's a 2D simulation.
The maser one.
It's 2D in real space, right?
It's 2D in real space.
See. So if you do 3D in real space, is there going to be any change? Or?
So we're resolving the components that are in. So what's going to change is how does the radiation look like far away from this source, because in 2D our radiation doesn't go down as 1 over r squared. But the radiation is, the growth rate are going to be the same, and the saturation may change. So we might have a bit lower saturation than what we're seeing here, by a factor of whatever it's. So I guess it'll be by less than a factor of 10, I would assume. Yeah.
Any other questions?
So I'm a bit confused about your magnetar picture. So your free energy is the transverse energy of this beam, right?
Yes.
So the cooling time will limit the pitch angle that you could sustain reasonably in this. And you would need presumably enormous Lorentz factor to explain the luminosity.
Lorentz factor in the perpendicular momentum, you mean? Or
Yeah.
okay, so.
Also, like, I mean, I would expect that interaction with any magnetic field perturbations in the inner magnetosphere would mainly, result in parallel motion rather than in transverse motion.
Well, but
so second step is also not super clear.
But why wouldn't you expect to pick up any perpendicular momentum if you are going through one of a turbulent, like, I mean, maybe we can talk afterwards because.
Well, you could pick up a cross B motion, but that doesn't result in radiation. And since the skin depth is larger than the Larmor radius, all of your kinetic wave effects would result in E parallel and would accelerate along the field rather than perpendicular.
Okay, maybe we can.
I mean, maybe, yeah, I'm confused about something.
Any other further questions?
Also, I just want to add quickly to that. This is just a bit of a cartoon as to how a heating could be produced, of course. But what I'm presenting here is kind of a fundamental process that whenever you have a hot plasma, you're going to produce this maser radiation. And so there are other ways of producing rings. Where, in fact, if you were paying quick attention to Arno's presentation yesterday when we had radiation reaction, you could see some rings on the back on the downstream. And so those could also be other places where this could be happening, just to adapt to that.
Yeah, very nice talk. Let's thank Pablo again.